Okay, guys, this is the first video on Gauss's law. We're going to go through the math and some of the mechanics of Gauss's law. At times, it's going to look pretty challenging what we go through because really, practically, the math can be pretty difficult when you consider that we have to do 3D shapes and calculus with three-dimensional shapes, and practically, it requires 3D vector notation or matrices that we might not be prepared to do. But you're going to see that the application that we use it for and the symmetries that are involved make this pretty simple for our particular cases. Okay, once you learn multivariable calculus and you look at 3D vector notation, Gauss's law can be done for many different geometries. But for us, there's only a couple of geometries we need to be able to do, and they're relatively simple. Okay, so at times this video might be confusing as we go through the mechanics. Just try to watch it a couple times, and then when you look at the application videos, I think you're going to see that it's not really that bad for what we need to do. Okay, so Gauss's law simply is this symbol here that I'm writing looks like an integral symbol. Then it has a circle in the middle, and very simply this means that it's a surface integral. Okay, a surface integral means that I'm going to be taking the integral over the entire surface of a 3D shape. So I'm going to draw some 3D shape that I'm going to call a Gaussian shape, and I'm going to take an integral over the entire surface. Now that's different from a regular integral, because a regular integral you're usually integrating a function, right? But if I think about a three-dimensional shape, well, a three-dimensional shape is not a function. Just like a circle on a two-dimensional graph is not a function because it doesn't pass the vertical line test. It has different y coordinates for the same x coordinate, and we know that's not a function. But a surface integral can be done over things that are not functions, like a three-dimensional shape, a three-dimensional surface. Okay, so I'm going to take the surface integral of E dot A. So this is the electric field. So I'm going to look at the electric field in all space dotted with the area vector. Very simply, the area vector is if you have a shape, like what I'm going to try to do here is a square that's sort of tilted away from us a little bit so that we can see the area vector. The area vector is the vector perpendicular to the surface of the area, to the surface of our shape. So the area vector always points out from the surface. This would kind of be like a normal vector. We know when we did normal forces only come out of a surface, and that's because in geometry the word normal means perpendicular to the surface or coming out from the surface. So this is what we would call our area vector. Okay, so just consider it to be always pointing out from the surface. Okay, so the surface integral of E dot A is equal to the amount of charge enclosed. So when you draw your Gaussian shape, however much charge you've captured inside of your 3D shape is right here, Q enclosed, divided by epsilon naught. And we should be familiar with epsilon naught. That is the permittivity of vacuum, or the permittivity of free space. Okay, so the first example we're going to do is with a point charge. So I'm going to go here and I'm going to look at the geometry and I'm going to show you we could make this difficult, we could really make this pretty challenging, or as long as we choose the correct Gaussian shape, we can actually make this really simple. Okay, so you're looking here at a point charge. Of course, we know the electric field of a point charge and what it would look like. It would go off in all directions, right? And we know what to expect. This electric field should be KQ over R squared. If we remember from doing point charges and doing electric fields, the electric field of a point charge was KQ over R squared. So let me take it here to where I can write on our screen. Okay, so we know to expect KQ over R squared because we've seen that before. okay? And we know that it goes off in all directions, so it is a 3D electric field going off in all directions, okay? Now I said for the Gaussian integral that the surface integral of E dot A is going to equal Q enclosed, how much charge have you captured, divided by R squared, okay? Well, this is all equal to what we call electric flux. Electric flux, okay? And that is the Greek symbol capital Phi for electric flux. And ultimately, you can think about electric flux as how many electric field lines go through my surface. How many electric field lines go through my surface? So the first thing I'm going to do is I'm going to draw a three-dimensional surface, what I would call a Gaussian shape, and I'm going to look at the electric field in and around that Gaussian shape. So the first thing I'll do is a sphere that is outside of my charge. Okay, so what I've done right now is I've drawn a Gaussian shape. And there's nothing wrong with what I've done, but I've drawn a pretty silly Gaussian shape, something that's not going to help me find the electric field due to the point charge. And the reason is I haven't captured the charge in my shape. So when I look at this Gaussian surface that I've drawn outside of my shape, I will notice that here I have one electric field line coming into my shape, and I have one electric field line going out of my shape. Okay? So in terms of the flux, how many electric field lines are coming into my shape? I've got a +1 here because one electric field line is coming into my shape, but I've got a -1 over here because I've got an electric field line that is leaving my shape. So overall, you would say that the electric flux for this Gaussian surface, this Gaussian sphere, the electric flux is 0. Now what that means is that if I go to this side of the Gauss's law equation, it means that I haven't captured any charge. In this space, I can confirm that there is 0 charge. And that's going to happen anywhere you draw a Gaussian shape without charge in it. The number of field lines coming in is going to match the number of field lines going out, and the flux is always going to be 0. If there is no charge inside, the flux is going to be 0. This does not prove that the electric field is 0. There is an electric field in this space. So you need to understand that if the flux is 0, that does not imply that E is 0. The only thing it implies is that there is no charge here. There is no charge in this space. So I need to draw a better Gaussian shape. I need to be a little bit more clever. So I'm going to do that by picking a different shape. Okay. So let me remove that guy and let me draw a random shape. Let me just make sure it's capturing the charge Q. So let me draw a random shape, and I've drawn a tetrahedron here, and I've got the charge inside. So that's great. At least now I know the flux is not 0. And I can tell you that because if this is a positive charge, then all these electric field lines are going outward. And because I've captured the charge, then that means at my surface, all electric fields are going out. There will not be any electric field lines going in to my surface. None, because this is a positive charge and I've captured the positive charge. So all electric field lines are going out. Okay, great. But what have I done? This is really difficult when I consider the other part of Gauss's law, and that is the surface integral. The surface integral of E dot A. It says, go around that entire surface. Go over the entire surface of your Gaussian shape, my tetrahedron. And at every point on that three-dimensional surface, take the dot product between the electric field and the area vector, which means only look at the part of the electric field that is parallel to the area vector. Okay? Well, I've drawn a tetrahedron, and the area vector for each of the sides, of course, is going to point, perpendicular to the surface. But what that's going to do is it's going to mean that all of these electric field lines all over that are penetrating each side of my tetrahedron are going to be at an angle to the area vector. So area vector, electric field line, they're not already parallel. So that means throughout all space, throughout this entire surface of this three-dimensional shape, when I do E dot A, when I try to only look at the parallel components, there's going to be a cosine of theta introduced at every one of these dot products. It means also that I would need a equation for the area vector of the tetrahedron all over this space in 3 dimensions, plus I would need to write the electric field function as a 3-dimensional function of kq over r squared in 3 dimensions, and then I would have to do the dot product between them. And that's really, really challenging, really, really difficult. The same thing happens if I try to get a little bit more clever and draw a sphere, but I don't have my sphere centered. Imagine I draw a sphere like this that is off-centered. It's capturing the charge q, but because I haven't drawn the center of the sphere at charge q, notice that the area vector, right, perpendicular to the surface, and the electric field coming through the surface have an angle between them. They're not parallel. So here, A and E are not parallel. So again, I've made the calculus really, really hard. I've made that surface integral so difficult that I need new math that I'm not familiar with, like 3D vector or 3D vector notation or matrices. And this is really, really tough. So I'm not ready to do that. But I can save myself a little bit by being clever. What shape could I draw around this point charge so that the electric field and the area vector are parallel everywhere? And of course, the only shape that you could do this with would be a sphere that is centered at the origin or at the point charge. Now you notice that in all space, the area vector and the electric field are already parallel. So everywhere, even in 3 dimensions, all throughout this sphere, the area vector and the electric field are going to be parallel. So that means that over this entire surface of the sphere, E dot A contributes everywhere. And if it contributes everywhere, this surface integral becomes really, really simple. It becomes the electric field times, because this dot product contributed everywhere, you picked up the entire area of the sphere. Over the entire area of the sphere, E dot A was simple. So what is the area of a sphere? Well, I've drawn it at a random arbitrary radius. So I'm going to use little r here for the radius of my sphere, because had I drawn the sphere a little bit larger, and that's not a very good sphere, but I did that by hand, had I drawn it a little bit larger, all the same results would have applied. I still captured Q. The electric field is still parallel to the area vector everywhere. So really the size of that R is arbitrary. So the area of my Gaussian shape, I would say, is 4 pi r squared. That's the area of a sphere. So that surface integral actually becomes really, really simple. It's just the electric field times the area of a sphere. And I said that that's equal to, again, this is electric flux, is equal to the charge enclosed divided by epsilon naught. Well, when I drew my Gaussian sphere, how much charge did I enclose? Well, I just had this 1 point charge, and it was a charge of Q. So this becomes E times 4 pi r squared is equal to Q over epsilon naught. And that's pretty simple. So what I'm going to do is I'm going to take that E times 4 pi r squared is equal to Q over epsilon naught. And the one thing I'm going to do here is I'm going to move over the 4 pi r squared. So electric field is equal to Q over 4 pi r squared times epsilon naught. That's what the electric field is everywhere at the surface of this sphere. In 3 dimensions, the electric field is Q over 4 pi r squared times epsilon naught. But hey, wait. I expected it to be KQ over r squared. So let's do this again. Let me rearrange slightly. E is equal to Q over 4 pi epsilon naught times r squared. But wait, what is K? K is just 1 over 4 pi epsilon naught. So E is indeed, we have this 1 over 4 pi epsilon naught. E is indeed KQ over r squared. Okay? All right, guys, so that's it for the point charge. This is something you already knew, KQ over r squared, but maybe you didn't know where it came from. And it came from this idea right here of Gauss's law. And again, Gauss's law can be really difficult, but if you're clever and you choose the right Gaussian shape, it can be really, really simple as just writing down the area of your shape, as long as you choose a good shape. Okay? Let's take a look at a couple more videos after this, some applications. Again, watch this a couple times until it makes sense, but really the application isn't that difficult. All right?